In this presentation, we will explain trends in relative nuclear stability. We will identify common particles and energies involved in nuclear reactions. We will recognize common modes of nuclear decay, and we will identify common particles and energies involved in nuclear decay reactions. Spontaneous changes to unstable nuclei are considered nuclear decay. The unstable nuclei is the parent nuclide, and the result of the decay is the daughter nuclide. The most common modes of nuclear decay are alpha particles, beta particles, and gamma rays. Alpha particles and beta particles are sometimes called alpha rays and beta rays. Alpha particles are positively charged and will bend toward negative charges. Beta particles are electrons and will bend towards positive charges. Note that beta rays are bending more than alpha rays. This is because of their weight. An alpha ray weighs a lot more than a beta ray, and so it deflects less. Gamma rays have no charge and do not alter course in an electric field. Radioactive decay is a spontaneous process that happens to unstable nuclei. We know this. What predicts the stability or instability of those nuclei? Let's take a look at the graph on the right. Has each isotope neutrons versus protons. So the first trend that we will notice is that at low atomic numbers, we have this 1-to-1 line, so a slope of 1 right here. This 1-to-1 line fits perfectly for very low atomic number. So as we go up, that trend no longer works. Higher Z's, it gets closer to a ratio of 1.5 or 1.52 to 1. And if you get to the point where the nuclei are heavy enough, there are no stable isotopes. We don't have any black up here. Why is that? Most of those compounds have been made using particle accelerators. We need neutrons in order to make the protons more stable when they're bunched together, all those positive charges. And there just aren't enough possible protons that we could put together to make that work. Okay. Now, we do also have what's called the belt of stability. It's clear in this graph that the stable isotopes are in black and they're surrounded by the unstable isotopes. So we call that the belt of stability. Go up the middle. The stable ones are in the middle. There are some other trends to what makes an isotope stable. Protons and neutrons fill shells in the nucleus. That's right, we have shells for electrons, but we also have them in the nucleus for protons and neutrons. Full shells contain 2, 8, 20, 28, 50, 82, or 126 protons and neutrons. Past hydrogen, we need some neutrons to have a stable element. So for example, helium-3 and helium-4 are stable isotopes with 1 and 2 neutrons respectively, but helium-2 is unstable and has 0 neutrons. Now elements with both numbers for protons and neutrons as magic numbers are called double magic. They are incredibly stable. So for example, we have helium-16 where we have 8 protons and 8 neutrons. We have calcium-40 which has 20 protons and 20 neutrons. And we also have lead-208. This is one where we don't match numbers, right? It's obvious. 82 protons, 126 neutrons. When we look at a trend for all elements on the periodic table, most of our stable elements, a full 157 of them, have an even number of protons and an even number of neutrons. So that is a favorable result. We have an additional 103 stable elements where we have an even number of protons or an even number of neutrons. There are only 5 stable isotopes with an odd number of protons and an odd number of neutrons. They're not very popular. The most common type of decay we already talked about, alpha, beta, and gamma rays. But in addition, you can also emit a positron, a proton, or a neutron from your nucleus. Alpha particles are composed of 2 protons and 2 neutrons. Beta particles are electrons, and positrons are positively charged particles with the same mass as an electron. Protons have an atomic mass of 1 and are positively charged. Neutrons have an atomic mass of 1, but they are neutral. And gamma rays are high-energy electromagnetic radiation, so think a wave. The symbols for these particles are sometimes represented in more than one way. So for alpha particles, we use a designation of helium-4 isotope or the lowercase Greek letter alpha. Beta particles and positrons also have 2 symbols. They can be represented as E for electron or lowercase Greek letter beta for the beta particle. Positrons are positively charged particles with the same mass as an electron. We also represent them with an E or a beta to indicate that they have the same mass, but we give the charge there. Okay, antimatter has the same mass with an opposite property. So in the case of a beta particle versus a positron, that property is charge. So you can have matter and antimatter pairs with other variations, but we are not particle physicists and we don't need to know that. Beta particles are considered matter, and positrons are considered antimatter. Protons are given as hydrogen, 1 isotopes, or with the letter P for proton. Neutrons are represented with the letter N, and gamma rays are given by the lowercase Greek gamma. So, as we can see, we're going to need to know this stuff in order to balance our nuclear equations. This will come up again. As previously stated, the most common modes of nuclear decay are alpha, beta, and gamma radiation. These are intentionally named after the first 3 letters of the Greek alphabet, as they were named in their order of discovery. Alpha particles tend to emit from heavy nuclei when A is greater than 200 and Z is greater than 83. The daughter nuclide has a larger neutron to proton ratio than what you started with. So if you look at our band of stability graph over here, alpha emissions are represented by yellow. And you can see that yellow is below the band of stability for almost everything. And then once you reach a certain point, things are not stable and you still have alpha emission. So there's some exception to that, but not much. Beta particles happen when the nuclide has a large neutron to proton ratio and therefore is above the band of stability. The emission of a beta particle results in the conversion of a neutron into a proton. So the daughter nuclide therefore has a smaller neutron to proton ratio than the parent. Blue is the color of beta decay on our band of stability graph. And as you can see, blue is above the band of stability, and once the beta decay happens, we'll move closer to the band of stability. Finally, gamma decay is when a nuclide goes from an excited state to a ground state. So gamma particles have no charge, have no weight, and so when you look at the balanced nuclear equation, you actually start with an excited state, which we give by a star. So we have a nuclide with a star of cobalt-60, and then it becomes just cobalt-60 without the star, so it's in its ground state, plus our gamma decay. This is probably the only time that you will see this notation. I'm going to be honest, it's not on the ACS test. I may give you one example just for shits and giggles, but yeah, that may be the last time you see it ever if you don't take physics. But wait, there's more. We have positron emission when the neutron to proton ratio is low. So therefore, the daughter nuclide of a positron emission has a larger N/P ratio than the parent. A positron emission results in the conversion of a proton into a neutron. So on the band of stability graph, the positron emission is in orange, and you can see that the isotopes that emit orange are all below the band of stability. Well, almost all below. Finally, we can talk about electron capture, which is the decay of an electron from its wave function into the nucleus. These happen when the N to P ratio is low. So a core electron is captured by the nucleus, creating a new neutron. The daughter nuclide, therefore, has a larger N to P ratio than the parent. An example of this is in the equation as follows. So we have potassium-40 capturing an electron, so that's our beta, and becoming argon-40. To summarize, the unstable nuclei is the parent nuclide, and the result of the decay is the daughter nuclide. The belt of stability is the stable isotopes that's in the middle of the unstable ones. Magic numbers can help you predict when you have stable isotopes. They are for full shells of neutrons and protons. Full shells are at numbers 2, 8, 20, 28, 50, 82, and 126. Elements with magic numbers for both protons and neutrons are double magic. Examples include helium-16, calcium-40, and lead-208, which is one where your neutrons and protons do not match, but both have magic numbers. There are several types of nuclear decay. The most common are alpha, beta, and gamma radiation. And we also have positron, proton, and neutron emissions, but all of them have particular symbols and can happen given the right circumstances.